Today, we're going to pull back the curtain on a system that powers so much of our digital world, from the maps on our phones to our favorite video games. It's a secret, universal language that lets us pinpoint any location with absolute precision. So let's dive in and see how it works.
I mean, have you ever really thought about it? You punch in your address, and somehow a driver navigates through a huge city and lands right on your doorstep. How on earth does the system know exactly where there is?
Well, the answer isn't just the street name you type. It's what that address gets turned into, a set of coordinates. You see, this system gives every single point on a map its own unique name, and today we're going to learn how to speak its language. All right, so here's our game plan for today. We'll start by figuring out why we even need a system like this. Then, we'll build the grid ourselves from the ground up, learn to speak the language of location, explore its different neighborhoods, and finally, see how it all clicks together in practice.
Okay, let's start with the most basic problem. How do you describe the exact location of a single dot on a flat surface, like, say, a computer screen or a piece of paper? It's actually a lot trickier than you might think.
Right. If I just put a dot on a whiteboard and asked you where it is, you might say, oh, it's kind of in the middle, but a little to the left. That's just not precise enough. For a computer or a GPS or any kind of map to work, it needs an exact, unmistakable address for that dot. And that is exactly what this system provides.
The solution to this whole location problem is a brilliant and surprisingly simple grid system, which we call the Cartesian Plane. It was invented way back in the 17th century, and it gives us the universal framework we still use today. And you know, there's a great story behind it. The legend goes that the philosopher and mathematician René Descartes was just lying in bed, watching a fly buzzing around on the ceiling, and it hit him. He realized he could describe the fly's exact position at any moment just by measuring its distance from the two walls, a simple observation that literally changed mathematics.
So the foundation of this whole grid is just two simple number lines. First up, we have the x-axis. Just picture a number line lying down flat. Numbers to the right of the center point are positive, and numbers to the left are negative. Simple as that. This axis controls all our left and right movement.
Next, we bring in a second number line, but this one stands straight up, vertically. This is our y-axis. Here, the numbers above the center are positive, and the numbers below are negative. And this axis, you guessed it, controls all the up and down movement.
Now that exact spot where these two lines cross is incredibly important. We call this special point the origin. Think of it as our universal starting point, our ground zero. Its address is always 0, 0, and every single other location on the grid is measured from this spot.
Okay, so we've built the grid. The stage is set. Now let's get into how to actually use it. This is where we learn to speak the language of coordinates, which are really just the unique addresses for any point we can imagine on the plane.
An address is always given as a pair of numbers, like 5, 4. And here's the golden rule you always have to remember. X comes first, always. The first number tells you how to move horizontally, and the second one tells you how to move vertically. So, to find 5, 4, you start at the origin, move 5 units to the right, and from there, you move 4 units up. Boom, you've found the exact location.
Now, for a little bit of the official lingo. The x-coordinate has a fancy name, the abscissa, and the y-coordinate is called the ordinate. Now I know, it's easy to mix those up, but here's a little trick. X comes before Y in the alphabet, right? Well, abscissa also comes before ordinate.
And this right here, this brings us to a really crucial concept, the true geometric meaning of coordinates. The x-coordinate isn't just some random number. It actually represents the point's direct perpendicular distance from the y-axis. And in the same way, the y-coordinate is its distance from the x-axis. See how it's always the distance from the opposite axis? That's the key to really understanding this whole system.
So when our x and y axes cross, you can see they slice the entire flat plane into 4 distinct regions. Think of them like 4 different neighborhoods on our map. We call these quadrants, and each one has its own set of rules.
As you can see, they're numbered using Roman numerals, and they go counterclockwise, starting from the top right. So we have quadrant I, quadrant 2, quadrant 3, and quadrant 4. And each of these quadrants has its own unique signature.
This table breaks down the sign rules perfectly. In quadrant I, up in the top right, both the x and the y coordinates are positive. Then moving over to quadrant 2, x flips to negative, but y stays positive. Down in quadrant 3, both x and y are negative, and finally, in quadrant 4, x is positive again while y is negative. These signs are like a super quick way to know which neighborhood any point lives in.
Okay, but what about the points that aren't really in a quadrant? What happens if a point is sitting right on one of the lines themselves? Well, there's a very simple rule for these special cases.
Just think back to our definition of coordinates as distances. If a point is sitting right on top of the x-axis, what's its distance from the x-axis? Well, it's 0. And that's exactly why its y-coordinate is always 0. The same exact logic works for the y-axis. If a point is on the y-axis, its distance from that line is 0, so its x-coordinate has to be 0.
And there you have it. That's the whole system. We've gone from a vague idea like top left to a precise, universally understood address like -3, 2. This elegant system makes sure that every single point on a flat surface has one and only one unique address.
So the next time you use a map app, or you play a video game, or even see a designer moving things around on a screen, you'll recognize that invisible grid they're all using. Now that you know its secret language, where else are you going to see it at work?